Good morning, good afternoon, good evening to everyone. Welcome to our session at Simon Fraser University. Today, we are going to have a very distinguished speaker to talk about graph theory. And before our introduction to our speaker, I would like to mention a few things about our discrete math seminar at Simon Fraser. Our seminar has been lasting for 20 years. And right now, it is every Wednesday morning Pacific time. I'm now putting the link to our seminar into the chat. So if you are interested, you can check it out. Associated with the seminar is a group, a very active research group on discrete math at Simon Fraser. And I'm glad to see many group members being with us today. So very nice to see you all. And if possible, please turn on your camera so that we can make it a little bit like our in-person seminar in the old days. I would like to mention the generous and continuing support from the Pacific Institute for the Mathematical Sciences. So PIMS has been funding our seminar since it was started. So we really appreciate that. I shall now hand it over to Alexandra Wesolek, another organizer from SFU, and she will introduce our speaker.
Thank you, Shuxing, for also the nice introduction. Before I'll introduce our speaker, I just wanted to acknowledge that although we are in Vancouver here, these are actually unceded lands of the Musqueam, Squamish, and Tsleil-Waututh people. So I'm very excited to introduce Chung. Chung is a distinguished professor of mathematics and computer science at University of California, San Diego, where she holds the Paul Erdős Chair in Combinatorics. She's a leading graph theorist and combinatorialist with broad research interests, including Ramsey theory, spectral graph theory, quasi-random graphs, and complex networks. She has authored nearly 300 papers and a few influential books, and served in the editorial board of many international journals. Among numerous honors and awards, she has been a member of the American Academy of Arts and Sciences, a speaker of the Noether Lecture of the American Mathematics Society, which honors women who have made fundamental and sustained contribution to the mathematical sciences, a fellow of the American Mathematics Society, and an Euler medalist of the Institute of Combinatorics and its application. And this last award recognized her distinguished lifetime career contributions to combinatorial research. Thank you, Chung.
Well, thank you very much for the kind introduction. I want to thank the organizers, the local organizers and the global organizers for organizing such a wonderful meeting. Well, I will talk about trees and forests in Green's function of graphs. And of course, for trees and forests, we all know pretty well, but I believe not too many people knows about Green's functions. Well, let me see how it works here. Okay, so we're concerned about not only trees, but spanning trees. In fact, rooted spanning trees. And the spanning forests, in this case, in this picture, is two connected components. And when we say two rooted forest, really means each connected component has one root at some specified vertex. On the Green's function, named after George Green, from this seminal paper in early 19th century. And I did a Google search about Green's function, and you can see it's pretty widely used, quite a popular terms in many areas, particularly differential equations and so on. When it comes to graph theory, what does it mean by Green's function? Basically, it's a pseudo inverse of the Laplacian, or its variations of the Laplacians. And Yao and I started looking into we call discrete Green's function or Green's function for graphs since 2000. So it comes from, of course, Laplacians. And as you know, Laplacians first came up in many other traditional areas. Nowadays, Laplacians for graphs comes in for a while. And this is an outline of the talk. So we'll more or less cover the first part, and then we'll go into combinatorial Laplacian and its origin in electrical networks, and see how Green's function comes in. And then we'll go through the normalized Laplacian. Then we have matrix tree theorem, matrix forest theorem, and we want to discuss how trees and forests and their enumerations coming in connection with Green's functions. There are various applications. I might not be able to cover too much, but we certainly will do heating time a little bit, and also its relation with ranking. Okay, so we are having basically two kinds of Laplacian. The combinatorial Laplacian here, L, is D, the diagonal degree matrix, minus A is the adjacency matrix. The normalized Laplacian, basically you normalize with respect to the degrees. So, and you can see it is equivalent to identity matrix. Okay, here we go. Identity matrix minus this term here is really transition probability matrix. So normalized Laplacian is very much related with random walks or diffusion type problems. Combinatorial Laplacian, on the other hand, is very good for counting problems, particularly counting trees, among other things. The volume of certain polytopes. And the normalized Laplacian comes heavily when we are concerned with convergence of random walks, or the bottleneck of the graph, or clustering, identifying the community, that kind of situation. Let me see. So for combinatorial Laplacian, really rose very early in electrical network theory. So basically you can imagine that at one vertex, we inject one unit of current, and at another vertex here, we eject a unit of current, and all the edges really representing, well, there's a resistance involved. And the early classical and very elegant electrical network theory, as the Kirchhoff law means, which is the conservation law, incoming flow equals outgoing flow. And Ohm's law, which means the current is proportional to the difference of the voltage and also proportional to the inverse of resistance. So if we assume all the resistance is 1, then put these two laws together in order to determine the voltage function f at each vertex. It is just the Laplacian comes in. So it's LF plus this boundary situation, right? The injection and ejection of the current. So it comes down to solving the system of equations. So in this case, if we have the way to solve it is basically getting the inverse of L, right? If any. In this case, well, it's not invertible. So that's why we're talking about pseudo inverse. If you look at the Rayleigh quotient, then you can see there's eigenvalue 0 just by taking all the f to be the same value. So if f is a constant, then that's the eigenfunction or O1's vector, okay? And the eigenvalues of the Laplacians here already, the first one, if it's strictly greater than 0, already, if and only if the graph is connected. So here, I'm not going to go to that spectrum too much, but because we want to focus on Green's function. So when you have such an equation that you want to solve, like the electrical network situation, then you can just, if we know the Green's function, which is a pseudo inverse, it's an inverse restricted to the space orthogonal to the O1's function, then we know how to solve it. And you can figure out this projection. Then if we know the Green's function, then we solve all these Laplacian equations, right? So another way of looking at it, our Laplacian is like, it's symmetric, so it has a spectral decomposition. So really, we just can decompose it into these eigenspaces. And the Green's function is just take the inverses of these lambdas. Sort of a pretty simple formula here, but that's not our goal. Our goal is to find the combinatorial interpretation of Green's function. Anything goes through spectrum, sort of going through a black box. We use Maple or MATLAB solving it, and we are handed our eigenfunctions, eigenvalues. So as a graph theorist or combinatorists, we like to get the combinatorial interpretation of it. And that's actually the main focus of this talk. We are actually going to go for one more generalization, actually two more generalization here and here. So, well, my pen is beyond myself. Okay, so actually my pen is very far away, but it seems to have a free will. So basically, if we have a scalar t between 0 and 1, then we have these more general, these general form of Laplacian with like t times identity matrix plus the Laplacian or the normalized Laplacian. And these, what we are going to do is to get combinatorial interpretations for all these Green's functions. And you are going to see it really means quite some interesting counting of trees and forests. After all, it is a very naturally arising kind of function is called Green's function, right? So such things usually should be beautiful in themselves. Okay. So as we know, so when we are talking about Laplacian matrix tree theorem, it's the classic by Kirchhoff very early. And I believe every graph theorist knows about this quite well. The number of spanning trees in a graph is equal to the determinant. Well, there's a typo here, of any cofactor of L. So here is an example. For this little matrix, we have this little matrix corresponding to this small graph on 4 points. We can see that matrix tree theorem told us that we are going to, there are 8 such spanning trees as illustrated here. And it's not hard to see that tau, the number of spanning trees in the graph, is just the product of all the non-trivial eigenvalues, if G is connected, divided by N, okay? So, okay, so you can see there are eigenvalues 2, 4, 4, and 0. So we should get rid of the 0, and you multiply them together, divided by N, which is 4. We are getting our 8. And in fact, if you look at the characteristic polynomial of L, and look at these coefficients of the characteristic polynomial, then the matrix tree theorem is this linear term, A1, which is the number of spanning trees times N, and if we are counting rooted spanning tree, that's exactly what it is, okay? And if we go up to K, it's the number of K-rooted spanning forests. It's a spanning forest with K connected components, and each component, exactly one vertex is marked as root. And if we count all these configurations, that's the number AK. So we go back to our example, you can see A1 is 32 because there are 8 such spanning trees, and if we put roots on, then each one has 4, right? And it happens to be a coincidence that A2 also 32. And I actually drew them all here with these roots. So you can see each little graph has 2 orange roots, and 1 in each connected component. Okay. Now we are going into Green's function, right? I use the script G to denote the Green's function because we only have 26 alphabets, and G is used too much. So we are using all these different scripts. Okay, so together with my student, Ji Chen, recently we have this result. The Green function UV for 2 vertices U and V. You can see N is number of vertices, tau, the total number of spanning trees, and the sum is over all 2 forests with UV in the same component versus the second sum, UV are in different connected component. And in particular, if U equals V, there's a simpler formula as a special case. If we do the trace, which means we sum over all the diagonal terms of G, of the Green's function, Green's matrix. Then we got a simpler formula, 1 over n tau times the number of 2-rooted. I think there's a typo here. Should be number of 2-rooted forest. Sorry about that. Okay, so here, see, I'm not going to give you the proof, tedious proof. Instead, I would like to convince you by example. So here, there is this little graph here, has eigenvalues. So we know the trace should be, trace of G is the sum of reciprocals of 2, 4, and 4. So we get 1. Well, the number of 2-rooted forests, very sorry. I have a pen, I can correct it. This is forest. Okay, I'm happier. Okay, so you can see that there are 32 forests in my previous view graph, and I plug that in, indeed I get 1. So although I think that at least it's a piece of evidence, so we'll have some confidence in this formula. Heating time. Heating time occurs in random walks. So it denotes, so QUV for 2 vertices U and V, it is the expected number of steps for random walk with starting point U and it first hit V, first hitting V, okay. So with this definition, we can get recurrence. So if U equals V, it's 0, okay. It's already there. If it is not 0, with probability 1 over du, so you take 1 step to your neighbor, then whatever the heating time from that point back to V with 1 more step, right? So that's the recurrence here. That's the recurrence here. So if we put that into the matrix form, then we get this equation, and you have to adjust the diagonal term with the so-called returning time, how long it takes for a point to go back to itself. So in our first paper in 2000, we actually derived this formula for the heating time in terms of the Green's function. Okay, here volume really means the sum of the degrees. The degree is what contributed to the volume. We stick with that definition. Okay, so for subset, the volume of S here is just sum of degrees for vertices in S. We also have this formula to explain the heating time. Sort of clean also. It's 1 over tau summing over these two forests when U and V are in different parts. But we summing for each one of these forests, the term we sum up is the volume of T1. Sort of not so convincing when I tell you this, but instead of giving you the proof, then again, let me go to the next slides if I can. Somehow I couldn't advance my slides. Okay. Sorry about a technical difficulty. Somehow, here we go. Here's my example. You see for this little star, I can directly compute the hitting time with probability 1/4 is 1. And then with this probability takes 3 steps and so on. So you get 7. On the other hand, I'm looking at 2 trees, U in one and V in another. There's only one such tree. And then it's volume T1, the volume of where U is at. So here we see that for this piece, so it is 7. So I am trying to convince you by example that this formula is actually of some good. Okay, what about the normalized Greens function, the script G? Okay, we have a more complicated formula, and the diagonal term is a little bit simpler. So it is, the trace is actually came down to quite nice. So here I'm going to do a check to make sure we are actually honest. Come back to our graph. So the normalized Laplacian is right here, and the eigenvalue, easy maple, gives me these eigenvalues, so I can compute the trace, which are the reciprocals of these 3 terms, come down to 47/20. On the other hand, I'm going to use the formula above. So each two forest contributes the product of the volume of 2 parts. So I marked all these volume T1 times volume T2 on the side. And at my first try, I got the numbers down, and amazingly or unsurprisingly, it comes also to 47/20. Okay. Not to mean by proof by example, but it's just one way to sort of trying to convince you that this formula is doing some good. How about this generalized Greens function? It's related with pagerank, which is a general version of random walks, but with this additional parameter. One reason I point out pagerank is because pagerank can be computed super fast, very, very efficiently. So Greens function, in spite of, as you can see, it has many terms. It's a sum of many terms, and each term involving, we are going to count trees and forests in connection with this Greens function. Nevertheless, instead of counting exactly, if we allow ourselves to approximate, it can be done very efficiently through this connection with pagerank. So let's see how it goes. So we have basic definition of random walks, the transition probability matrix, and we're going to use lazy walk. This is the original definition of pagerank in this classical paper of Bring and Page, Sergey Brin. So you can imagine a surfer, a bored surfer, either surf a random web page with probability alpha, or a neighbor, visit a neighboring web page with probability 1 minus alpha. So there is this alpha involved, sort of controlling the rate of dispersion. So if you put this into an equation, then it's exactly this recurrence. Here, P denotes a row vector, and our W is a matrix, right? So this is a row vector. For random walk problem, as you know, the multiplication is coming from the left. So if another way to write it, instead of the uniform distribution here, we put the, I think my pen is not exactly working. Okay, instead of this S here, uniform distribution, we put in the a seed, some given distribution, usually very often localized. So in that case, well, okay, so like 1 at one vertex and 0 elsewhere, a different initial distribution. Okay. So if we take this recurrence and move things around a little bit, then you can see at the bottom, the Greens function comes in here. So the pagerank really is sort of equivalent to the Greens function. Okay. So here is a picture one of my students did a while ago. And the good thing about pagerank is that it can be analyzed, and the running time's extremely fast. For if you fix an approximation and fix this, you can see the running time is almost really too good, independent of n. Okay, so with that said, I want to give you the trees and forests in the Greens function, okay? We actually are counting a lot of trees and forests in our Greens function. So so Greens function is no longer a code term. It involves all these familiar subjects, trees and forests that we all love. Okay, so here we are actually doing weighted version on this slide. So for each edge, there's a weight. And for forests, the weight of the forest is just the product of all the weight of edges in the forest. So in the usual simple graph case, it is just 1. Really, it's just counting. Okay, and then for rooted tree, we have to be a little bit more careful. We have to quotient off those product of degrees, right? Not roots. So if we agree to these definitions, then this is, we can write it out. See the normalized, the generalized script L beta here is not invertible if beta is strictly non-zero. So we can take determinant and all these k-rooted spanning forests coming in, okay. And if we look at the minor, then it has some similar forms, okay. And we can use all that to derive the Greens function. So you can see it's sort of string together. So we always like to think about connectivity as actually in some papers, the reliability of graphs or the edges was counting trees, how reliable a tree is, okay, proportional to the number of spanning trees it contains. But it's beyond that. It is two-rooted spanning forests or the k-rooted spanning forests. They all string together to make up our Greens function. So in spite of such a sort of a large sum, if we want to count exactly, there are so many trees, so that's a lot of complexity, right? However, to approximate it, as long as you give an error term, that epsilon, then the whole thing can be computed, can be approximated within that epsilon very efficiently by going through pagerank. Okay. And there are, here I am not going to go through specification. I only want to say one thing. The one thing is that, see, the Greens function as assigning a value, a positive value to all edges. So what does that mean? It means we are really ranking the edges. Every edge is associated with positive value. The value reflects how important or unimportant it is. So the specification was using this in order to choose edges randomly as the specification of a graph, satisfying the situation that the specification and the original graph should have the same spectrum. It can be approximated within epsilon, what every one of the eigenvalues, not just one, and which is pretty strong condition. As you know, there was a lot of progress in specification, especially for the work of Spielman and then and many others. Okay, I'm not going to get into that, but I just want to point out the Greens function really provides a ranking for all the edges, which is also the same as the pagerank. Pagerank really, instead of graph distance to define how close two vertices are, it is a much finer matrix. It's a value. Okay, I want to say, I want to mention some problems. Okay, so here, so this is the, before I talk about the problem, let me first do this one. Okay, so what happened is that some time ago, this is sort of a page on this newspaper saying that close the 42nd Street in New York City, and somehow the traffic got better. You close off one street, somehow it's sort of against intuition. The traffic got better. So the graph theory version is that in a graph G, is there a subgraph with fewer edges, right? But turns out to be better. So what do I mean better? Okay. So I'm going to color the edge red. If we delete the edge E, the resulting graph has a large spectral gap. This spectral gap is the normalized Laplacian, okay? If you don't do normalized Laplacian, you do usual graphs, then you have the, interlacing theorems. It's a different story. As I say, normalized Laplacian really has more direct connections with the bottleneck of the graph, the shape of the graph. Otherwise, for usual two graphs, if you delete one edge, you can see the largest eigenvalue definitely going down. The spectral gap, very often, if your graph is not regular, then the spectral gap has a lot to do with the largest 2 degrees. Okay, and the spectral gap of the normalized Laplacian, the lambda 1 and 0, that spectral gap has everything to do with convergence or random walk. Okay, so suppose we use that definition, a graph is better. See, for normalized Laplacian, all the eigenvalues are normalized by degrees. So it's between 0 and 2. So there's a way to compare versus combinatorial Laplacian. Combinatorial Laplacian, the values, the range of the values depending on the maximum degree, really. So in essence, they are not so comparable. So when we want to compare two graphs, in this case, we, at least here, as this problem is formulating, the spectral gap is the spectral gap of normalized Laplacian. So we mark the edge red. If it's really, if we kill it, the graph is better, right? So some time ago, I posed this problem in a random graph. How many red edges? How many edges are actually by deleting them, your graph is better. Okay. So at that time, I get my students to compute. So for every edge, generate a random graph. I think GMP. So 50 vertices. 50 choose 2. There are a lot of edges, so it's have to compute quite a bit to figure out how many red edges you get. So it's actually, amazingly, a very large fraction. More than 40% of the edges are red. You are better off without them, okay? So 9 out of 10 simulations. And then there's a 100.1, okay? So, okay. So at that time, it was a conjecture made saying that for random graphs, dense random graphs, of course, you get a substantial fraction of the red edges. And this conjecture still stands. Actually, recently, I'm trying to put even a stronger one. C is a half. And after I give this talk, I think at Simon's Institute. So later on, I was told they prove a version of the problem. Instead of deleting, they are adding a random edge. And what is the probability that that edge is redundant? So they have a log by 1/8. However, more and more evidence sort of pointing out the C is that I believe it's C should be a half, but of course it's a conjecture. But now, since we rank the edges, since we give a value to every edge by Green's function, I want to say, look, look at that edge with the least value in the Green's function. Throw that one away. The graph should be better. So I'm going to just post this as a problem here. I think I am approaching the end of my talk. And thank you all very much for listening.
Thank you very much, Chung, for this beautiful talk. Maybe we could unmute ourselves and clap. Okay, now we have a couple minutes for questions.
I have a question. It's a great talk. And with these red edges, are you seeing any correlation with the degree sequence? So for vertices of high degree or low degree, are you seeing more,
Well,
more or less, or is it not really a local thing?
Basically, we are talking about GMP, and P is a half. So it is almost regular, right? Although in our computation, it was a small example.
Yeah, so it's off by square root of n, but then there's a few vertices a little bit higher. So that those deviations aren't large enough to see something more substantial, you think, or is it really too close to regular?
It was not the. It was, in fact, the program my student read was not that sophisticated. It doesn't pick out the analysis of the bad edges. Yeah. It was just counting.
Thanks.
I have a question. So, Fan, you have displayed many magical formula throughout your talk. So my question is, how could you came up with them at the first place? By some experiments or just by good intuition?
From my part, it was actually simpler. I was trying to make some problems for my students.
Okay.
Yes, and I always know that the matrix forests, matrix tree, I always love matrix tree theorem. And I don't know how many papers I wrote about matrix tree theorem, many different versions. And of course, in this is really a generalization of all that. In spirit.
I see.
Yeah.
I see. Yeah. Thanks.
Thank you for the talk, Professor Ben Chung. I have a question about the regarding the complexity. So counting, given a graph counting the number of spanning tree is polynomial time solvable, but if we count the number of spanning forests is sharp-P hard, sharp-P complete.
I think it is the same as counting trees. It is just instead of a minor, you just cross off 2 columns and 2 rows for the 2 forests. So the complexity is the same level.
Okay, right. Thank you.
Yeah, good to see you.
So Fan, so
yes. Hi, Peter.
How are you doing? So one of the ideas you might try to use here is deleting these edges in order to improve mixing time for a random walk. But of course, if you just delete edges, it changes the stationary distribution.
Yes, exactly.
But you could ask instead. Yeah. But you could ask instead to look for a pair of parallel edges and switch them.
Ah, that's a good idea.
Yeah, Jacobs is nodding his head. Yes. So that distribution is kept with the idea of improving the spectral gap. Thoughts on that? Or?
Yes, that will be interesting to figure out the rules of how things are exchanged, right? There are a number of these switching games. Well, that's a very interesting comment. Thank you, Peter.
I'd like to see somebody try that in New York, switch 2 of the streets.
Yes.
Another question, how do you think about the Hodge Laplacian?
I actually see that there are many different directions to go. And some of it are, you know, especially you go up, you go up to higher dimensions, then there are these signs involved. So instead of the usual hypergraphs are really all positive sign, versus in Hodge, you know, the sign plays a real role depending on the orientation and so on and so forth. So there are many different directions to go there, which I didn't mention that, those higher dimension Laplacians.
Okay, thank you.
Too many questions.
Yeah, indeed, very interesting questions and insightful comments. So we have to stop here because we need to spare some time to hand over to next session. Let's thank Fan again for the great talk. Thank you.